Okay. So we will start. Uh, Cannot get this to work. Hey Siri, restart this device.
Just to
So I have to wait a minute. Okay. So I've logged in. So let me present. Okay. Okay. Week number 9. So we will look at the lecture materials first, and then we continue. So I'm audible, right? We have seen transformers in NLP, or maybe we have not. I don't think I have covered in the previous lecture. I just touched upon it. So let's see what are these here. So we are moving to vision transformer. So just for understanding, we first need to know the uh, the NLP one, okay, NLP transformer, the original transformer, okay. So so the paper name is attention is all you need. So this is the paper here, so which introduced the transformer architecture for us, and so this is the transformer architecture. So first we have to define the attention here, okay, and the attention is dot product based, okay, and let me download this one. Okay. Okay, I already had it, okay, so open that one. This is the paper. So here you can see this is the transformer architecture. We'll get to that later. First, we need to understand what is attention. Okay, little bit of understanding is required. So attention that they have defined here. So this is called the scale dot product attention. So what is you have here is that Q, K, and V are there. Okay, query, key, and value. Okay, so what these things are, let us understand that. Okay, so let us first take a sentence. Okay, uh, say I am a good boy. This is the sentence we have here, and well, let's not damage the paper here. Let's take it somewhere else. Okay, so what will we have here is that so say I am a good boy, and so you can have tokens of each of these words, okay, and then token can be, so token is the a discrete form, okay, and the token can be further represented as a embedding, okay. So let's say you have a embedding of size 612, okay. So each word uh, can be represented as a token, okay, a visual token, means language token, and then can be represented as a vector of dimension 612, okay. So the values 0, 1, 2, 3, 0, some values, okay, and these are so the tokens form a dictionary, okay, whatever the tokens that are possible, okay, or maybe the words you can say in simple terms, okay. So they form a dictionary, and and uh, and each token in the dictionary can be represented in the form of an embedding, that as you call the dimension of the embedding is 612, so it is a vector of dimension 612, okay. Now so what you have, so I can be represented as like that, am can be something else, okay, like that. Now you stack them together, okay. So this I one, then am one, then a one, then good one, then boy one, okay. So So you stack all of this together. So what you get is a so what is the dimension of this? So this is 612 multiplied 5. So this is the dimension, and you can represent it as a matrix. Okay, some values are there, 1 point something, 0 point something. Okay, like that the values are there. So you join the embeddings together and they form a matrix. Okay, and this matrix is called the query matrix. Okay, and the key query value all are of the same value, all are the same actually. Okay, they are not different. Okay, and so this is it is. Okay, so this is what it is. Okay, so this is q, k, and v, all are of the same values. Okay, so these are, and of the dimension in this case is 612 cross 5. Now what you have here is so this is the embedding matrix. Okay, you have, and now the attention is softmax of q transpose. Let's go and see. So it's k q k transpose under root dkv. So the attention has been defined as, where was I? Okay, so the attention has been, this is making it hard to see. Okay, so the attention here is q k transpose under root dk into v. So now what if you do q into k transpose, what will you get here? So q dimension is this 612 cross 5, k dimension is 5 cross 612. When you multiply it, you get a matrix of dimension 612 cross 612. Okay, so this dk is called the or dimension of the model. Okay, which is 612. So dimension of the embedding is equal to dimension of the model, is equals to dk. Okay, and so this is it. Okay, so what happens is that if without scaling, when you multiply these two matrices together, what can happen that that so you can understand when you're using softmax, so what you're doing is that okay, so let's understand what is happening. So this softmax we are doing. Okay, and the thing we need to understand, the scaling happens so that they can be so scaling happens because in softmax the we raise it to the power e. Okay, and if we don't scale, okay, some values may dominate. Okay, okay, so now so this is called the attention. Okay, and this will define which and suppose the so what happens is that when your query is I, suppose, so it is called self attention. That's also important. Okay, I, okay, now it searches over which word token is important for I to occur. Okay, so that is what this product is defining. Okay, and okay, so this is what we have here. This is called self attention, and further we see that so they form a multi-head attention. What that means is that they divide each of the the model demodel dimension into suppose 4 or 5 parts. Okay, subsequently the matrices are also divided. So what it means is, you go here, you go here. Yeah. So suppose 612 is divisible by 4. Okay, so suppose we have 4 heads here, so that becomes 1, and so you divide by 4. So what it becomes is, first 306. Okay, and divided by again dividing by 2, so 5 3 153. Okay, so and each of this can gets divided by 4. Okay, and now the 4 of the attentions are calculated of each of the 4 head, and then what they do, uh, so then what they do is they concatenate each of the head. Okay, and so for, you can see first of all, so attention of each head is calculated here. Okay, and then what we're doing is, okay, we're concatenating the heads, and then we have a weight matrix as well. uh, so this so you can see here that, so we have a learnable matrix here to actually make it into several heads. So what they're doing is that they are multiplying each of the KQV with a learnable weight matrix, as you can see this one. uh, and so you can see the dimension. So the dimension is d model cross dk, as you can see. So what happens is that, q is of the dimension, uh, so it was like d model into length of the sentence. Okay, but I think they have considered is in the opposite direction. So for length of the sentence into d model, so when you multiply it with d model into dk, the dimension becomes length of sentence into dk. Okay, so each of the uh, dimension gets reduced. Okay, we finally also multiply with another learnable weight matrix w0, take it back to the original dimension. Okay, so this is what they do here. So this is called the self attention. Now further, as we move, so here we see that, so the input is, the, suppose, so it is popularly used for a sequence to sequence translation. What it means is that suppose you're given an English sentence, you want to translate it to French. Okay, so what happens, you are, so first this is a like a supervised approach. So you are given the English as well as the French one. Okay, and you feed both. Okay, so English one goes in the input and the French one goes here. Okay, and so they also use a positional encoding here. So in the paper they have defined a sinusoidal positional encoding, according to which the, so you can see it in the paper. Yeah, so here it is. So for each position, and for I is defined as, I is the dimension. Okay, so embedding have different dimension as well, right? So for each position and for each dimension, um, so it is giving some value position encoding. So this is one way. Another way is to use learnable positional encodings. Okay, so that's another way to do it. Okay, and so there are two ways. So there are two ways here. So you can use a sinusoidal position encoding, or a learnable embedding, okay, which will act as a encoding while it trains. Okay, now what happens is that uh, so it is given to multi-headed attention, okay, and it learns the attention, and then so this attention, so what happens is that it learns the embedding actually. Okay, so the embeddings are then transferred into add and norm, and then into feed forward network. Okay, so one of the embedding also comes here. Okay, for this cross attention, this is called cross attention, and the self attention part is same here. So now the cross attention happens, so the q comes here. Okay, kv are here now. So cross attention happens and then leads to newer embeddings, and then it goes to feed forward network, add and now, and you finally get the softmax output, which predicts which is the probable uh, token to occur. Okay, so this is the uh, structure of this attention and transformer. So now we'll okay. So now we'll go to our this. Uh, so where we're looking at, I think week 8. Actually, week 9. This is the one, no? So, attention serves various purposes, and you can learn machine translation, language understanding, and these sort of things. Okay. Further, so these are some of the NLP tasks, and these are the NLP models that are there. Okay, and you know some many of them. So requires a sequence of vectors as input, so that the embedding we have discussed. So these are the different problems we have here. So we cannot use pixels as token, because then our computation blows up. Okay, so actually what will happen is that we will make tokens out of patches. Okay, so that is we will consider an RGB image of size this. So they make patches here. Okay, linear projection to d-dimensional vector. Okay, so they make it a linear projection. They use a linear layer and they project it into a d-dimensional vector. Okay, some position in embeddings, learnable, this time learnables, okay, are also added. Okay, so we're actually going to the vision transformer domain. Now this is same as the NLP transformer situation. So you have these embeddings which is fed into the transformer. Okay, so and it gives output vectors. Okay, so that is how it is. Okay, okay. So here in vision transformer, so this is the structure as you can see. So patch plus positional embeddings are input into the transformer encoder. So we also maintain a class embedding. Okay, so what happens is that the class of the image is input as a CLS token. Okay, and so what happens, whatever, so the consider understanding is that, so after we get the embeddings, the embedding of the class token, the first token, it goes into a MLP layer. Okay, and the output, so it is something like this. Okay, so HCLS, the embedding of the CLS token, and these are the H patch. Okay, patch I, so of every patch, so one patch, two patch, the I patches. Okay, and there is CLS token. Okay, so which is to be used for classification. Okay, so this is the thing we have. And and this embedding of the CLS token is used for okay, so embedding of the CLS token is used in a linear layer. So HCLS is multiplied with a linear layer. So this is the linear. So this A and B are trained. Okay, so you get Z. Okay, so in the back propagation, A and B you can compute. Okay, so you get Z out of it, and is Z then is put into a softmax. Okay, so from Z we calculate the softmax. What it means is that the dimension of the Z is of the number of classes. Okay, so what you do is that you calculate the softmax, which is Zi plus by summation of e to the power Zi by summation of e to the power Zi. Okay, so this is what we call softmax. Okay, okay, so from that, so softmax can be taken as a probability. Okay, so highest probability of occurrence of which class that we will get. Okay, so this is what we do here. So the here the linear projection is a convolution, they say. Okay, with stride being the patch size. So so the stride of the convolution is equal to the patch size. Okay, so what happens is that then the representation you get does not mix between each of the patches. Okay, so the representation of each of the patches different. Okay, so the MLP they have said is a stack of 1 cross 1 convolution. So the I had shown the original MLP how it is. Okay, uh, but what you have here is a 1 cross 1 convolution. Okay, so 1 cross 1 convolution is as good as uh, a linear projection, right? So that is what it is. Okay, the vision transformer versus ResNet. So we calculate the classification accuracy here. So as you can see here, so they do a self-supervised pre-training on the data set, on the data set. These are ImageNet 21K, JFT 300 million. Okay, and and uh, and then we calculate the accuracy here. So you can see in ImageNet, the ResNet has the highest accuracy, the VITR of the lower value. Okay, but subsequently you can see that when the size of the dataset increases, uh, okay, then VIT does better. Okay, and and as bigger the VIT, the bigger better is the performance. Okay, this we can see easily. Further, you can see that so these are VIT huge of 14 layers. Okay, the 14 transformer layers one after another applied. Okay. This is regularization and augmentation. So, so there are so they do some augmentation to the image as well for self-supervised learning. Okay, that happens. Okay. Okay. So then they represent the distillation loss. Okay. Uh, so what they do is there is student teacher network. So teacher network is a large CNN, and student network is a VIT. Okay. With this you can improve the VIT performance. Okay, so VIT is a small architecture. So it learns from the trained teacher model. Okay, and the loss is a cross entropy loss and KL divergence loss with teacher outputs. Okay. So further you can see that VIT versus CNN comparisons are there. So the in most CNN include ResNet, resolution decreases and number of channel increases as we go deep into the network. Okay. So this is what is there. So in VIT, all have the same architecture. All blocks of the VIT has same architecture. Okay. So we get the same resolution. So they also define another type of transformer called the Swin transformer. So what Swin does is a type of hierarchical vision transformer. Okay. So what you see here is that the image you have here. So this batch partition. Okay. So batches are formed. Then it goes to linear embedding. Okay. So the embedding of the patches are formed, and then it goes to a Swin transformer block. So it is not explained what is Swin. Okay. So let's go and see. So it is broken into smaller patches and projects. It is projected linearly into from a 48 dimension to C dimension. So that is what they have done, and so that is the linear embedding. So we've reached up to this point. Okay, then it is fed into a Swin transformer block. So what is Swin? Let's see that. So patch merging. So what we see here is that so they merge. So you have H by 4, W by 4 cross C dimension patch here. Okay. Now what we do here is that so what you do, you take you make one half of that. Okay, and then stack it top of one. You make it half. Okay, so you stack this one on top of this. Okay, like that. So like that, if you do, so you get something like this. Okay, understood? Now and so it will become 4 times. Okay, okay. If you take each of this and stack. Okay, so then it will the dimension become 4c, right? So project linearly into 2c dimensions, from 4c to 2c dimension. You use a linear embedding for that, linear projection layer. So you now the input is this. Okay, further the input is this. Okay, so they have not explained what is a swing transformer. Okay, that is what we see here, but you can understand it like it's a type of hierarchical transformer. So what happens is that hierarchical transformer means that uh, each of the transformer block learns different tasks. Okay, the focus, the attention um, is on different level of task. Okay, so that is what swing transfer is for. Okay, maybe they will define. Let's see. Oh, architecture details are there. So with H cross W grid of tokens, attention matrices are of size uh, H to the power 2, W to the power 2, which is a quadratic in image size. Okay, so this is the problem we have. The solution that we propose is the window attention. Instead of allowing each token to attend to all other tokens in the image, divide image into window of M cross M tokens. So we divide into smaller patches. Okay, and okay, so that's what to do. The compute attention with each window. Now the attention matrices are of size m squared hw, which is linear in image size for a fixed m. So Swin uses m equals to 7 throughout the network. Okay, and it is linear in image size, means image size h is h into w, so that is the size. Okay, with window attention, there is no communication between windows, restricted to the flow of information across different regions of the image. So then they do shifted window attention. Okay, so these are actually the policy that is used to train the swing transformer. Okay, shifted window attention, and okay. Okay, we'll get back to this. Okay, let me take a break, 5 minutes break. Okay, then we'll come back to this. Okay, so let's focus. Uh, so these are the brown ones are the patch, and these red ones are the local window. Okay, so the layer 1 you are having a bigger window size, and layer 2 you are having smaller window size. Okay, so shifted window attention, that is what is they call. So, and exactly how what is that? Shift the window attention progressively across the image in a hierarchical manner, enabling interaction with the patches across different level of abstraction. Okay, so they're shifting the windows of window, and so that leads to attention between different patches, which did not happen without shifting. So this helps in capturing long range dependencies while maintaining computational tractability. It is crucial for applications such as image classification, object detection, and semantic segmentation. So here, the architectural detail is shown here. So you can see that. So so this is the layer normalization, windowed and shifted window configuration of self attention, WMSA, SWMSA. Okay, these are there, and then multi-layer perceptron. Okay, so these are the window uh, self attention. Okay, and this is the shifted window, SW. Okay, so these two are applied so that it can learn long range dependencies and how every patch is related to the another patch. So what happens in that, in the previously when we were having patches, so each pixel was interacting with another pixel in another patch, but so they mix up the patches. Okay, so mix up the attention area, so that leads to more robust learning and leads to long range dependencies. So this positional embeddings they're talking about. So it does not use positional embedding, instead it encode relative position between the patches when computing attention using learned biases. So that is what it does. It uses learned bias, which is the relative position between the patches. Okay, attention with relative bias is defined as this. Okay, so in transform speed versus accuracy comparison. So the accuracy, as you can see, Swin has the highest. Okay, at every so it we're looking at the processing speed millisecond per image. Okay, um, so so as you can see, as the processing speed improves and the accuracy further improves. Okay, in each of them, but Swin has the highest. Okay, task specific vision transformer. Swin serves as general purpose backbone for diverse vision tasks, including this. In addition to Swin transformer, recent advancements have seen the emergence of task-specific transformer detailed for various vision tasks. That is, detection transformer, especially designed for object detection tasks. DETR replaces traditional convolutional network with transformer-based architecture. Segment anything. SAM focuses segment anything tasks, leveraging transform architecture to effectively capture spatial dependencies and context information. It was proposed by Meta. Okay, so you can just point. You can open the website. Okay, and maybe I should show you. if you click this one, so 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 as you can see, it can segment the image. Okay. And suppose if we try the look distant image of this tree, will this also work? It's not selected. What it is showing? uh, so this is you can play around with it. Okay, so it can segment easily. Okay, now what you have here is this. And other notable examples: clip for vision language task and swin IR for image restoration. Okay, this is what we have here. And okay, now now let's go to some of the questions here. Get the questions here. Maybe I have not downloaded. So in the vision transform architecture, the following design choices primarily help in capturing the spatial dependency across the entire image when patch embeddings are processed. So spatial dependency is talking about why this method is considered more effective than convolution kernel in traditional KNNs for large scale data set. The use of learnable positional embedding added to patch embeddings. So special, okay, multi-header self-attention mechanism which allows patch to attend to every other patch in the image, ensuring global receptive field, and that increases the model's ability to capture long-range dependency. So B is the answer. Okay, that is easy enough, right? So as you can see, A does not capture the relationship between the patches, between the embeddings. Okay, so it just ensure which places the patches. So let me get some water. So so you have an input image of size this. Okay, so I'm not able to write here. So this is the answer here. So next we have an image of size this and split into non-overlapping patches of size this. Each patch is then flattened and linearly projected into 768 dimension embedding space. What is the total number of learnable parameters for this linear projection layer? Okay. So this is the question we have here. So what you have is that so it is first made patches of this. Okay. Then it's flattened. Okay. So 16 into 16, how much is it? And 256, right? So this 256 dimensional matrix we have here, okay, vector we have here, and it has to be transformed into a 766 dimension. Okay, okay, you understand? So how many total number parameter learnable parameters for this linear projection? Okay, so they're talking about linear projection. So say z is this z, this is h. Let's say so a h into b is equals to z. Now they have told to ignore the bias term. Okay, so number of parameters, number of learnable parameters in A is the answer. So A has to have x cross this h has to match. Okay, 256 dimension. Okay, and you have to understand uh, and this dimension is 768 multiplied 1. Okay, this is 256 cross 1. Okay, okay, and so you understand, for it to be 768, it has to be 768 as well. So the A dimension is 768 into 256. So the total number of learnable parameters is quite large here. Am I wrong? No. This is the answer. Okay. Got it? How it is done? Understood? Okay. Moving on. No. Sure. Okay. So Ahana, you can unmute yourself and help me out here. What you have not understood, if you may. Yes. You can ask the question.
Actually, the image size is 224 into 224.
Yeah, yes, yes,
So patches are 16 by 16. So you have multiplied 16 by 16 and then you have multiplied with 768.
yes.
But how does this give the total number of learnable parameters?
That's a good point.
But what
So, so what they are saying is that so you must understand this linear projection layer. Okay. So this linear projection layer, what it is doing is that uh, so 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 it has two parameter a and b. Okay, so they have told to ignore b first of all. So already a is there. So take it as a linear layer. Okay, a linear learnable layer. So what it is doing is that it is um, fed the patches. Okay, so the total number of patches can be how many? 224 by 16. How much is
Mm-hmm.
it is? So it is 11256 and 28 14. 14, right?
Yes, sir.
14 is the number of patches possible. So all of these patches are fed into the same learnable uh, linear layer. Okay, so and each of them will be transformed into this 768 cross 1 vector. Okay, so it is
Mm-hmm.
not like that for each patch we have a linear transformation layer. For all of them we
Mm-hmm.
have only one. Okay, you understand? So why is that important? How did I understood that and we were not able to? So the thing is that so you must understand. So for it to train, it has to generalize over all the patches. Okay, that given a patch, it is able to generate the dimensional space, 760 dimensional array. Okay,
Mm-hmm.
so for that it has to be trained over all the patches. Okay, and given another new image with a different patch, if it is fed into the linear layer, it should still be able to produce this embedding dimension. You understand now?
Yes, sir.
Okay, so for each of them there is a single linear layer that they have to go through. Okay, understood, right? Okay, so let's continue here. In the Swin transformer architecture, the introduction of the shifted window attention is a key improvement over traditional vision transformation. The following is the primary advantage of the shifted window attention mechanism. It enables each window to attend to every other window across the improving models able to capture global context without increasing the computational complexity. So A is the answer, I think. B is the answer. Okay. Uh, okay. From shifted window attention alternates between non-overlapping and overlapping windows. Okay, that is what they say. Actually, it does not allow to attend to every other window directly. Okay, this is the thing. Okay, now so you're working with a swing transformer here. Possess the input image of size 224 cross 224 using a window size of 7 cross 7 for the window based self attention mechanism. The transformer operates at four hierarchical stages with patch merging between each stage. Acha. Patches are merging and bigger patches are forming at every stage. The input patch is 4 cross 4. So if it merges, so what you get? Uh, so it's doubled in both height and width. Okay, so it becomes 8 cross 8. Okay. How many windows will be created in the first stage of the swing transformer when the window size is 7 cross 7? Okay, this is the question we have. So let's see the answer. So the image size is this. The first stage, the patch size is 4 cross 4. This means the image is divided into patches of size 4 cross 4. Okay, the number of patches we can find out is 56. Total 56 patches. Okay, so the now the window size is 7 cross 7. So in each window how many patches are there? Okay, so that is what we are uh, oh, so in each window, so there are for 7 on each rows. Okay, is there, and so it means 49 patches are there in each window. Okay, so first the total number of patches we can understand in the image is 56, right? uh, Correct here. Yeah, 56 cross 56. Yes, that's important. Yeah. And now the window size and composed of 7 cross 7 patches. Okay. Now the number of windows in the first stage is, okay. Now you understand that along each column or each row, you have 56 patches. Okay, and you need to find how many windows are there on this along this row, and each window contains 7 patches, so divide by 7, right? So this is the 8 along each row, so multiply 8 along column, 8 along row, so there are total 64 windows. You can understand this one. And okay, so the number of windows in the first stage is this one. You can understand 64 windows are there. Okay. Any doubt? So what happens after each stage, the patches are merged and it becomes 8 cross 8, right? Patch size becomes 8 cross 8 of the second step. After the third step, what it happens is that it is again doubled, so it becomes 16 cross 16. Okay. Uh, I don't think it's patches of size 4 cross 4 becomes 28 cross 28. Let's see the problem again. Input patch size 4 cross 4. After each stage, the patch size is doubled in both height and width. Patch resolution is talking about. That is the same thing, patch size. Can anybody understand what is done here? I mean, should not be like this, right? So patch resolution is talking about. Cha 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 cha. Oh, okay, okay, okay. So patch size does double, okay, like this 8 cross 8. So this patch resolution they have said is the number of patches, okay. That is what it is, okay. So what you have here is that you can see, so this 224, if you divide by 8, what you get here is 28, right? So this is 28 cross 28, okay. So then it is divided by 16, okay. So they get 14 cross 15, 14, right? So this is the number of patches, okay. Number of patches along row and column. So multiplying them, you'll get the total number of patches, okay. After third stage is again divided by 2, okay. So it becomes 7 cross 2, 7 cross 7, okay. When you divide this, so if you do this calculation again, so what you have is so okay. So what they do is, let's see to that. So the number of patches becomes 7 cross 7. That's correct. Okay. Now, okay, okay. After the second stage, so after the second stage has done, okay. So then you enter the third stage actually. Okay. Uh, After two stages of patch merging, okay. So the third stage has not finished, okay. So after the second stage, you enter into the third stage, okay. And there the there you can see this is the number of patches 14 cross 14, okay. Now it is divided by this is the window size, okay. So the window size has become 7 cross 7, okay. So we divide by like that, and then we get 4. Actually I was doing it again, okay, and that is why I was getting the wrong answer, okay. So it has to be done 2 times, not 3 times, okay. Any doubt? My head hurts actually. So so we have the DTR model. So this is a novel approach to object detection by leveraging transformer direct set prediction. Okay, so this is just a architecture for specifically for object detection. Okay, so they have defined it like that. Yeah, I did it so badly that I cannot read now. Without relying on traditional methods like anchor boxes or non-maximum suppression, which of the following best explains the role of the bipartite matching loss in DETR? Why is it crucial for the model's convergence? Okay, so bipartite matching loss is the, so you can see. So they say the B is the correct answer. The bipartite matching loss ensures one-to-one correspondence between the predicted and the ground truth. Okay, so it is like so one-to-one correspondence. That is what they explain. So it is like you can say it like cross entropy loss type. Okay, or Gale divergence loss. And so segment anything model is there, which architecture choice allows to generalize across different input prompts for segmentation tasks. So I don't think we've gone to the details of this. So the C is the answer. The vision transform is there. Yeah, we have seen in this presentation that vision transform with dynamic prompt encoder that adapts based to the input. So when we are giving this, when I was touching the image actually, so it was giving a prompt on uh, which part of the image to uh, segment. Okay, so there is a prompt that it was giving. Okay, uh, so that is it actually. We'll cover rest of the things in later. Just very tired today. So any doubt up to this point? Any doubt? When will I cover Dino? Okay, okay. If you say so, then I can cover Dino today itself. So Dino is in the syllabus. Dino is not in syllabus. So what is the full form of Dino? Am I, if I have not been wrong? So it is actually a self-distillation method of self-supervised learning. Uh, okay, self-distillation method. Okay, and along with masking. So is that what you want to learn?
Yes, sir, it is there in one of the lectures.
It is there. Which lecture is there?
I think it is in transformers for detection.
Transformer for detection. Sure. Uh, let's check the lecture material then. So so in Dino, what happens is that uh, okay. So in Dino, what we happens is that it is trained using a self distillation method of training. Uh, this is the one. Dino is there for real, huh? Uh, just I believe you. I believe you. Dino is there. Okay. So let's go to the Dino paper then. Okay, and I'll explain from there. Okay. So let's learn what is Dino. So
So you got it?
so this is the paper, actually original paper from Facebook. That's what I opened. Okay. Uh, so just to give a brief, so okay, okay. People say Dino is there. Okay, so I believe you. Okay. So what happens in Dino? Okay, architecture, Dino type of self-supervised learning that. Just wait a minute. Okay, just week week 9. How did I save presentation? Week 9. Okay. So let's use this one. Okay. So what happens is in Dino is that this is the image you have. Let's say I. So it undergoes two transformation. Uh, Not two transformation. Yeah, two transformation. Okay. So suppose there is a group of transformation T. So you sample a transformation T here, and you get two versions of it. So this becomes X and Y. Okay. So after transformation it changes, right? So that is what I meant. And now they are fed into a self distillation network. So what is self distillation network? So you have two encoders here first of all. So am I going the right way? This is what is there in the lectures. This is what is Dino. If you are asking something else, I don't know. So this is fed into two encoder. Okay.
Okay.
Okay. Yeah. So this is fed into two encoders. Okay. And so one is called the teacher network, and another is called the student network. Okay. Now the student network. Okay. So you get some representation out of it. Suppose let's say this is like zx and this is zy. Okay. So you get two representations out of it, zx and zy. Okay. So what happens is that you compare the two representations here. Okay. And so this is done using a cross entropy loss. Okay. Now one more thing we have to understand here is that uh, and so what happens is this student network is so this is structured. Okay, and you have a cross entropy loss here. Okay. Now the student network is the student are say with parameter theta, and this teacher network with parameter phi is there. Okay, so these are the different different parameters. The models have different parameters. That's what I meant. Okay, so theta is updated using back propagation. So this loss you'll find here, concentrated loss, that is back propagated to update the theta. Now this phi parameters is updated using a slow moving exponential, slow exponential moving average of this parameter of the student network theta. Okay, so this lambda is equals to 0.00 something like this. Okay,
Mm-hmm.
it is updated slowly. Okay, this is called the self distillation architecture. Okay,
Mm-hmm.
so further what happens in case of this dyno, the teacher network is also a online tokenizer. So what it means is that uh, the the loss is defined in the token space. Okay, so what is token? So yeah, the image is divided into patches. Okay, and yeah, and for each patch the token is learned. Okay, so this is a teacher network for self-supervised learning, and it's also a online tokenizer. Okay, that is how it is defined. And this the token in case of vision is so each token represent a distribution. Okay, so in case of in NLP, a token is a deterministic value. Okay, but in case of vision, it is a distribution. Okay, like this. So the value is stochastic, not deterministic. Okay, and so for each patch we have a token. Understood? Now, so now what they do is that so they employ a masking strategy on the patches. Okay, and so you have two images. Okay, so you understood. Okay, so you employ masking on that. Okay, so what it means is that for okay,
Mm-hmm.
so the
Okay.
masked image, so this is let's say masked image of, let's say this is masked image of, let's say present by I am X. Okay, a masked image, so some of the patches are masked. Okay, and this is I am Y. Okay, so this is how it is fed. Okay, and now in the student network you can see, so it is not masked. Okay, so I represent by I N M X, I N M Y. Okay, so this is how it is fed. Okay, and you are also, so it is also fed with a CLS token for classification. Okay, so to distinguish between both of the images. Okay, so this is the structure. Okay, it learns to produce the token. Okay, so what it means is that, so so it learns to produce the token, and what it means is that, so so each token here. Okay, so the output is a token, it in this token space. Okay, this was in the batch, this is in token. Okay, so output is in token space, and first what you do, so this is this two representation. Okay, one is output from the teacher network, one is output from the student network, like that. Okay, so this is for let's say image X, and this is for Y. Okay, hope you got it.
Yes, sir.
And and this is from teacher network. So this is let's say image X from teacher network, so XT, let's say, and this is image Y T. This is image, this one, image X student image, and this is actually not an image. Okay, it is a in the token space a representation factor. Okay, and this is a I. This is student, and this is what is it? Y. Okay, understood. So, so when you feed x into this student teacher, so you get two embedding, and then you feed y. So now you must understand that. So if this is the same thing, okay, okay. So, so so let me be clear here. So first, what we do here is that these two are same, right? These two are same image, and these two are same. Okay. So what you do is you apply cross entropy loss. So cross entropy loss is applied popularly for a classification problem, right? So you apply cross entropy loss on each of these and add it together, uh, because the CLS token has the classification code, so that will differentiate between x and y. Okay. And another thing you do is, for each of them, okay. So
Mm.
what here we have is this the masked image, masked tokens that you get. Some are masked, some are not. Okay. So 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 this so this you take. So the unmasked part, so you take cross entropy loss between each of the patches here, each of the patch tokens as well. Okay, and add them over. So there are total, suppose n patches are there, so you add over n, and here you will have the unmasked one, and here you will have the masked one. Okay, in cross entropy loss you will have the probability of probability distribution, which is unmasked one, then it is the masked one. Okay, for each token there are n tokens total. Okay, you do it for this one as well, and then add them over. This is the total loss function, and this is the structure of the dyno. Another thing they do in dyno is they is centering and and centering and scaling. Okay. So this calculation is done over batches. Okay, so you in a batch you have several images. Okay, so over a batch you calculate the mean. Okay, and you subtract the mean over a batch. Okay, similarly you calculate the standard deviation and subtract divide by the standard deviation from each of the image batch. Okay, so this is required so that it does not collapse into trivial solution. Okay, and okay, so this is it. And this mean is the mean, this one is required so that it does not collapse into a deterministic one solution. Okay, that this representation dominates, this token dominates. It does not happen like this. So it does that. This sigma level it up. Okay, so it uh, okay, now I got it wrong. The sigma avoids this overconfident. This token is the supreme one type of direct delta. It avoids the direct delta one. Mean avoids the that it collapses into a mean solution when every one of them are of equal value. Okay, so this is they do to avoid the representation collapse. Okay, this is dyno for you. uh,
Okay, sir. Thank you.
Thank you very much, everyone. So any more doubt?
Here it's a student teacher network, so student learns from the teacher. I just want to understand the losses like.
So what happens
So
is
what
that
happened?
hello, yeah. So what happens is that the what happens is the teacher sets the target for the student. So student has to match the targets of the set by the teacher. Okay. And so in the cross entropy loss, the truth value is given by the teacher and the prediction is from the student. Okay. So that is one important thing. But does in so in classical distillation, knowledge distillation, the student learns from the teacher as well. Okay. But here what happens, the teacher also learns from the student. Okay. So what happens is that when you're updating the parameters of the teacher network with a slow moving average, so what it means that when the student network is learning through backpropagation, the teacher is not putting effort to learn through backpropagation as well. It is just sharing the knowledge from the student. Okay. So it is also learning from the student. Okay. So this is a distinction between self distillation and knowledge distillation. In knowledge distillation, only the student learns from the teacher. In self distillation, both of these learn from each other. Okay. So this is something to
Okay.
understand. And the architecture also similar structure. In knowledge distillation, what happens is that the teacher encoder is of a very big size, while the student is of a thinner model. Okay. But in this case, it can be anything. The architecture doesn't matter. The size of the encoder doesn't matter. Okay.
Okay, but what student will learn that totally depends on how the student was trained, right?
Uh, so so the what student learns is from the loss, right? So because we back propagate
Okay.
the loss. Okay. And how the loss is calculated is a cross entropy loss. Okay. So in cross entropy loss, what you have is P teacher log P student. Okay. So this is the this teacher distribution is the target and the student distribution is the learned one. Okay. So PS has to match PT, not the other way around. Okay. Cross entropy loss ensures that PS reaches PT. Okay. So you understand now this, but the teacher is also learning from the student. Okay.
Yeah, that is understood, but how can we check that what is not learned by student?
So
Is there any?
so what happens with the student learns from the loss, right? By back propagating the loss, and the loss is defined as student matching the target set by the teacher. Okay, that is how it is. So that is how it learns. Okay, that is what it's called.
Okay.
Teacher sets the syllabus and student learn, something like that.
Yeah, but it also depends on the number of epochs, is it?
Uh, Epochs is important, yes. In any training, it happens iteratively. When you're back propagating the loss, it is happening after every iteration. Okay, so that is the thing. Epoch is important, yes.
Okay.
Epoch till
So that's
convergence.
what I mean. What is learned by student and what is not learned.
What is learned by student, what is not learned by the student.
So we still the ways. If the model is trained for certain epochs, then student will learn only that much representation. But after certain period, since we stop the training, it's not going to learn. So I want to understand what representations are learned or
So
what's not.
yes, so what happens is that you have to train it till convergence. What it means is that so you're trying to optimize. So the when you're trying, the loss function has both the parameters phi and theta. So phi is the parameter of the phi is the parameter of the teacher network and theta of the student. When you're trying to
Okay.
optimize the reduce the loss, reduce the loss, right? Loss has to be reduced. So it is trying to reduce both. Okay. And a situation comes when uh, when the collapse is about to occur in representation, what happens that one of the parameter phi or theta is really optimized, leading to a collapse solution. Suppose all token values is same, or one is maximum, others are zero, like that. And so one is optimized greatly, and other is not. So phi and theta, one of them, okay. But in when the ideal situation is that both of them are somewhat reduced, but none of them are totally reduced, okay. So it is like there is a so there is a um, like game between them, phi and theta, okay. But none of them are totally totally optimized, okay. But both in the loss function both are there, okay, but both cannot be optimized at the same time, okay. So it is done as best as possible, okay. So that is how it is. So it is similar to the GAN paper actually. GAN you cannot so the
Mhm.
generator and adversary is there, okay. You cannot optimize the parameter of both, okay. They will be in a game, and they will converge to a Nash equilibrium, not a minimum, okay. So same here actually, the concept is same here.
Okay, but our if our objective is to optimize the student model, not the teacher model.
So the
So do we
teacher,
have that kind of control? Like if I want to optimize student model or
so then
teacher
then
model?
it will not work, na. If you want to optimize the student model, the target is set by the teacher. So the student
Okay.
model get optimized, but what it works on is a untrained teacher giving random targets, okay. So it will not be able
Mhm.
to learn.
Okay, because you said we can't achieve both the things at the same time, phi and
So they
lambda.
resolve to a samjhauta, you can say. Both
Okay,
cannot be
equilibrium
optimized.
kind of a status. Mhm.
Yes, yes.
Okay, got it. Thank you.
Okay, thank you everyone. Any doubt? No doubt, right? So we break it off here.
Yes, thank you.